Okay, so now we're going to continue our discussion about enzyme kinetics. And so this requires a refresher about thermodynamics as well as kinetics. I have included on our lecture note module kind of a 1 to 2 page refresher about the essence of thermodynamics, very basic. To hit the high points. Okay, of course, this is not comprehensive. So these questions should be second nature to you as chemists and as biochemists because you've been encountering it probably since you were in high school in one degree or the other, and in every chemistry class since then. So when do we have a spontaneous reaction? Under what conditions? When delta G is negative, right? When it is an exergonic reaction. How do we define a system at equilibrium? Delta G, the actual free energy, is 0. If we have a positive and endergonic conditions, then what do we need for that reaction to go? We need to add energy of some kind to overcome that. We know that the Gibbs free energy depends on enthalpy, delta H, entropy, delta S, and the temperature. And does the thermodynamics actually provide information about the reaction rate? No, it does not. Okay. How can we relate our understanding of thermodynamics and kinetics? And I feel like these two concepts, ideas, really one struggles with them, or I certainly did, learning this material. And then all of a sudden, in the context of a different class or a different instructor or something, the light bulb goes off and finally it all makes sense. Okay. So I would encourage you to go back and revisit general chemistry textbook because that puts in words what you may perhaps be encountering in physical chemistry, which is a more sophisticated understanding using partials and with respect to this and that parameter. We will not get that sophisticated, but these terms you should already be familiar with. Our actual free energy, our standard free energy, the equilibrium constant, okay? The activation energy, delta G double dagger, enthalpy, delta H, entropy, delta S. And what does this mean? Okay, we do know that the relationship between the free energy is the difference between the enthalpy and the entropy, which is multiplied by the temperature in Kelvin, okay? And just when we talk about bonds breaking or forming, or intermolecular forces breaking or forming, that is the enthalpy term, okay? That is enthalpic in nature. So we're talking about delta H when we're talking about covalent bonds breaking and forming, intermolecular forces breaking or forming, okay? Recall, it is an endergonic process. Delta H is positive. It takes energy to break covalent bond. It is an enderthalpic process. Delta H is positive to break intermolecular forces, okay? Conversely, if you are forming a covalent bond, that is exothermic, delta H is negative. If you are forming intermolecular forces, hydrogen bonding, van der Waals interactions, ionic bonds, that is also exothermic, delta H is negative, okay? This should be second nature to you by now. Please go back and review materials from general chemistry and other classes in which you've encountered this. Okay. So let's consider a reaction of A plus B going to C plus D. Okay, and we can write with their appropriate stoichiometric coefficients. We can write the equilibrium expression shown here with the stoichiometric coefficients written as superscripts, okay? These are actually chemical activities rather than actual concentrations, just as a reminder of what you encountered in quant. For our purposes and the purposes of this discussion, to make it clearer, okay, we are going to ignore the stoichiometric coefficients, okay, for now. And as you well know from general chemistry, we can relate the standard free energy, delta G with the degree sign, to the equilibrium constant by the relationship of the gas constant and temperature in Kelvin, by this expression that you've known and have already used this semester as well as in other classes. Okay. When you first encountered the standard Gibbs free energy, we define that where the initial concentrations of the reactants and products are at 1 molar and the reaction is allowed to equilibrate. Okay, so the final concentrations at equilibrium are not going to equal 1 molar. Now, in biology and biochemistry, we have additional environmental conditions that we need to account for so that we can relate the standard state, okay, with just the degree sign to the biological standard state. That is, whatever the symbol is, Gibbs free energy, enthalpy, so forth. As the biological standard state has a degree sign and also an apostrophe. That apostrophe indicates it's the biological standard state. Okay, so in a similar fashion to the standard state, the initial concentrations of reactants and products remain 1 molar, okay? But the additional environmental conditions that must be taken into account to define the biological standard state is we are at neutral pH, pH 7, and this is an aqueous environment. So the concentration of water, even though it is not explicitly stated in the reaction, it is present and it is at a concentration of 55.5 molar. Okay, so that is inherent by the presence of this apostrophe. If we are using ATP as a reactant or a product, ATP, as we'll see in the next chapter in our discussion of myosin, just coming attractions, magnesium is often non-covalently complexed with ATP. So if ATP is involved, we also have the assumption that is inherent that a magnesium ion is present at 1 millimolar. Okay, so that if ATP is used, that is also implied by this apostrophe. Okay, the biological standard state, you know, just as we saw with the standard state, the reaction is allowed to equilibrate. And recall, at equilibrium, the concentrations of the reactants and the products do not necessarily, and in fact, are very unlikely to equal 1 molar, which is where we started out with our initial concentrations. Okay, so we can, again, this apostrophe for our actual free energy, our standard free energy, that apostrophe is present. Okay, I indicate the biological standard state. The biological conditions standard. So here's our actual free energy, our standard free energy, and the gas constant, temperature in Kelvin, and the Ln of the ratio of product concentration over reactants. This term, the products of reactants concentration, gives us the reaction quotient or the mass action ratio. This is a concept that you encountered in Gen Chem 1 or more likely in Gen Chem 2 and probably in quant. These are the non-equilibrium concentrations, okay? And this reaction quotient can tell you which way the reaction is going to go, in the forward reaction or in the reverse backwards reaction, dependent upon how the reaction quotient compares to the equilibrium constant. If these are words that are not making sense to you, please go back and read your general chemistry textbook. Okay, so these are the non-equilibrium concentrations. Delta G is the actual free energy of the reaction. Okay, so that is dependent upon the standard free energy as well as the actual non-equilibrium concentrations of products and reactants. Okay, so the spontaneity of a reaction, whether a reaction is going to go forward or not, depends on the actual free energy, that is the conditions on the ground inside the cell of the actual concentrations of products and reactants inside the cell, okay? It does not, the spontaneity of that reaction does not depend upon the standard free energy. Again, this should be a total review for you. Just cutting and pasting this reaction here. At equilibrium, delta G, the actual free energy, is 0. We do some rearranging and we get back to this relationship between the standard free energy and the equilibrium constant that you well know. Okay. We also know at equilibrium, again, from general chemistry, that it represents a dynamic equilibrium. That is, the forward reaction rate equals the backward reaction rate. Okay. So it's not a static equilibrium. Molecules are always being turned over from reactants into products, and vice versa. Products are being converted into reactants. So dynamic equilibrium. And as a reminder, at equilibrium, the concentrations of our reactants and products do not equal 1 molar. The 1 molar was only for our initial concentrations. Okay, so as a refresher, we compare our reaction quotient to the equilibrium constant, and that tells us which direct way the reaction is going to shift to obtain equilibrium. You did many problems about this with these ideas in general chemistry. Okay. It's really important to keep in mind that the standard free energy and the reaction quotient are both used through this relationship. Remember, this is Q, to actually calculate the actual free energy for the actual concentrations. So the boots on the ground, okay? And of course, we know when the equilibrium constant is greater than 1, this is an exergonic reaction. The free energy, standard free energy, is negative. When it is the equilibrium constant is less than 1, you know that that's going to be an endergonic reaction. And when equilibrium constant is 1, the products and the reactant concentrations are equal and the standard free energy is 0. Okay, and of course we use this form with the joules per mole Kelvin as our gas constant. This should be a completely total review for you. And this table just illustrates it just as a point. You do not need to memorize this. You should be able to calculate the relationship between our standard free energy and the equilibrium constant. Okay, so that's thermo in a nutshell. And again, I have that handy guide for you. But you're like, hey, Sheets, we're talking about catalysis, and that's what enzymes do. How can we relate this? Okay, this is the other piece of general chemistry, most likely general chemistry 2, that you spent a lot of time and probably agony learning about. So this is little k, the rate constant, okay, in contrast to the big K of the equilibrium constant. And you can see that it's a collection of terms of Boltzmann, the temperature, and Planck's constant, okay? And we are relating, there's this relationship between the reaction rate, small k, and the activation energy barrier, delta D, double dagger, okay? It's an exponential relationship. So we're talking about the activation energy, it's the hump that is going over, okay? We are not talking about the thermodynamics, the free energy of that reaction, okay? When we're talking, what a catalyst does is enhance the forward rate to the same extent as it enhances the backwards rate, okay? So K is not changing because the rate, the forward rate and the backward rate remain the same, are enhanced to the same degree, okay? If we plot a reaction in the absence of enzyme, okay, we see that, and we're plotting the product, the amount of product as a function of time, okay? In the uncatalyzed reaction, we see that there's a linear relationship of this product accumulating with time in a linear manner. And if we extend this out, we'll eventually see that we eventually generate quite a bit of product, okay, as indicated by this black curve. Now let's compare that to, and start to appreciate the beauty of enzyme catalysis, and that is shown here in this red curve, okay? You can see that it is hyperbolic in nature, okay? That there is an enhancement in the rate initially, and eventually there's a saturation effect, okay? We'll talk about these two characteristics in the next video or the one after that, but in this chapter, okay? So this happens at shorter time scales, and if we look further out at very long time scales, again, the black is the uncatalyzed reaction. You can see in the presence of the enzyme, the catalysis, they reach the same equilibrium point, okay? So the idea that we are going to drive home and come back to over and over again is that enzymes facilitate the formation of the transition state, and the formation of that transition state by the enzyme lowers this activation energy barrier, comparing the dotted line, the dotty line, with the solid line, the uncatalyzed reaction, okay? And of course, you know that depending on the specific mechanism of a given reaction, you can have different shapes to your reaction coordinate diagram. If you're going through in this left plot, forming actually a complex between the enzyme and the substrate and then the enzyme and the product, you can have semi-stable states, but you're still going over an activation energy barrier. The difference between the substrate and the highest peak is our catalyzed rate compared to our uncatalyzed reaction, okay? And if we think about the forward and backward reaction, we have our substrate over in this catalyzed, this is, we're going from our substrate to our transition state. That is this difference here. That is defining the activation energy barrier going from substrate to product, okay, in this forward reaction. The reaction free energy is the difference between product and substrate free energies. And if we're going in the reverse direction, the product, I mean, we're going from P to S, it's even a higher barrier, okay? So what's going on? If we can write our substrate, our transition state is the X double dagger, that is the transition state species, and P is our product. So we can consider substrate going to the transition state. We can define that as an equilibrium, big K double dagger, okay? And the only way we can get to our product, this is kind of, I want you to get conceptually what we're talking about on this page. You will not be using these equations at any point in this class, but it kind of sets the groundwork for our discussion when we talk about the Michaelis-Menten model, okay? So if this is really not so clear to you, that is okay. The Michaelis-Menten model, when we really put this into action, is where it's important, okay? But bear with me. So again, we have our transition state. The only way we get to product is through the reaction rate, okay? And this is going to be proportional to the concentration of our transition state. Okay. Our overall reaction rate is dependent upon the reaction rate constant that turns over from our transition state to product and our concentration, okay? By multiplying these two, this gives us our overall reaction rate. We can also define this again by this collection of constants, the substrate concentration, remember that this is an equilibrium, and this is also related to the free energy of the transition state, okay? If this did not make sense to you, that is okay, don't sweat it. We'll be coming back in a clearer fashion to the Michaelis-Menten model where that will be important. This is was kind of a little foray, probably into a cul-de-sac.